Okay, in this video I'd like to continue on with my discussion of beta decay. So this video clearly leads on from part 1, and I'm going to assume a lot of things. I'm going to do some quick revision of course here, but I'd suggest you look at my video on the standard model. I suggest you look at clearly the first video for this, and also look at my video, The Introduction to Nuclear Physics, because a lot of that will be needed for this. So I'm going to push through my revision pretty quickly, okay? So the first thing I'm going to do is just show you some notation. So any atom, we can call it, or any, when say any element, okay, we call it, we'll say X, or it could be C, or whatever it is, something in the periodic table. It can be described as follows. Its nucleus can be described as having an atomic number, which is the total number of nucleons, and a nucleon is a proton and a neutron. We have its Z number, its total number of protons, and we have its N number, its total number of neutrons. And we know the atomic number, which I said was equal to the total number of nucleons. That, of course, is going to be the number of protons plus the number of neutrons. I also told you that that an atom is always electrically neutral, and that means that the number of protons must be equal to the number of electrons. So the number of electrons is equal to Z also. So the next thing I'm going to do is talk about the decay processes. So I said in the past that a beta minus particle is an electron, and a beta plus particle is a positron, where these are antiparticles of each other. An antiparticle has the exact same properties as a matter particle, except that the charge is changed. So an electron, which is a matter particle, its antiparticle is a positron, which is the same mass, the same properties, it moves at the same speed, and it just has a different charge. And it's for historical reasons that we call them beta particles, in that when people started investigating radioactive decay, they said that there were beta particles being emitted because they did not know what they were, and eventually they found out that they happened to be something called electrons, which they already knew about. So if you're doing beta plus decay, that means you're emitting positive charge. If you're emitting positive charge from your nucleus, that means you're reducing the amount of positive charge in it, which means you're increasing your number of neutrons. And if you're emitting a beta minus particle, that means you're emitting negative charge, which is your electron. And if you're emitting negative charge, that means you're increasing your positive charge. Okay? So let's write down the formulae for the two of these conversion processes. So I'm going to do that in green. So for beta minus decay involves a neutron becoming a proton. How do you know that? Well, look, we're emitting negative charge, which means the positive charge must go up. Alright, so that means we're going from a neutron is becoming a proton. So if we have an element, any element like that, that element becomes a new element. So in this decay, the number of neutrons is reduced, the number of protons is increased, but the atomic number stays the same. In order to decrease the electric charge, the negative electric charge, we must emit an electron. And for quantum mechanical reasons, which you're not going to go into, and you should just accept these, we need to emit another small particle called an anti-electron neutrino. Now, by the way, this bar here is to the right. That means it's a negative charge. But this bar is on top, which means it is an antiparticle. So if you looked at my video on the standard model, you realize that this is a neutrino, that E means it's an electron neutrino, and that the bar means it is an antiparticle. So look, don't get bogged down on this. Just accept that this particle is also emitted. So if we're emitting a beta plus particle, that means we are emitting positive charge. So we're reducing a proton. So a proton is being converted to a neutron. So just to show you that, we start out with the element as follows, and that decays to A. We reduce the number of positive charge, we get a new element, we increase the number of neutrons, and we emit our positive charge, which is our positron. And we also must emit, this time, an electron neutrino. So this is an anti-electron neutrino, and this is just an electron neutrino. I also showed you how to get the masses of both the atom and the nucleus. So I said that the mass of a nucleus, m sub n, is equal to the number of neutrons times the mass of a neutron plus the number of protons times the mass of a proton. Alright, that's pretty intuitive. But I also said that the mass of the neutrons and protons on their own scattered around space is greater than that when they're put together in a nucleus, because of all the positive charge trying to repel each other. So energy must be expended to keep the nucleus together. That means we must reduce the mass by b over c squared. And we know that E is equal to m times c squared. So an energy divided by the speed of light squared is a mass. And this B here is the binding energy of the nucleus. Capital B is the binding energy of a nucleus divided by c squared, and you get the mass. We also said that the mass of the atom, which I call capital, or just m, excuse me, is of course the number of neutrons times the mass of a neutron, plus the number of protons times the mass of a proton, minus b over c squared, which is the binding energy of your nucleus. We now need to add on the number of electrons, which is z times the mass of an electron. But also we need to reduce once again the mass here, because the electrons are also trying to repel each other, and we do it by a small b over c squared, which is another energy. Alright? Now, just to tell you that the binding energy of the nucleus is much, much greater than the binding energy of the electrons. So oftentimes we say that the binding energy of the electrons is approximately 0. So if you see that term missing, don't worry about it. It's just that it's very small in comparison with the other terms. And also, we know that most of these terms here are actually taken into account by m sub n. So another way of writing the total mass of an atom is m sub n plus the mass, the number of electrons times the mass of the electron, minus b over c squared, like that. Now I suggest you write down those equations if you don't already know them, because we need to use those. So now let's look at beta decay. So when you're decaying and you're emitting particles, there's energy released. That is the mass energy which was being used to hold the atom together. Okay, or hold, we'll say, those particles inside the atom. Now the thing is, during decay, only the nucleus is affected. Alright, only the nucleus, only neutrons and protons. Okay, that's the first thing. So the mass and any energy that comes from a decay must come from all the neutrons or protons. Now when we say that there is an electron or a positron emitted, these are not orbiting electrons. Alright? It means, what I'm saying is these are created from energy during the decay process. And why that should make sense to you is, we know that positrons, which are the antiparticles, do not exist on the atom. So in order to see them, they must be created. And if you accept that, then you should also accept that electrons are created as well. These are extra electrons than the ones that are already orbiting, and they're emitted immediately, and they just fly away from the atom. Alright? So any energy that's being released, or any mass that's being released during a decay process, must come from the mass of the nucleus, and the nucleus only. So that means, let's look at the beta plus decay process. So the beta plus decay process, as I said, let's write it once more. It involves the following: that element decaying to a z minus 1, an a, and an n plus 1, emitting a beta plus particle, which is a positron and an electron neutrino. So let's look at the energy released. We know that E is equal to m times c squared. Alright, and we call the energy released during a decay a Q. Now it's still an energy, we just use the letter Q. It's not a big deal. Alright? So the energy release is very straightforward. It's going to be the difference. It's going to be, we'll say, the mass before minus the mass after. Or I should say the mass energy, because they're the same thing. Alright? The mass energy before minus the mass energy, E-N-E-R-G-Y, after. Alright? Now we're talking about only the nuclei. We're not talking about the whole atom itself. So let's have a look at this. Alright? So that means the Q value is equal to the mass of the nucleus of atom X minus the mass of the nucleus of atom Y. Alright? Minus the mass of this electron or this positron emitted. And I said the positron is the same mass as an electron, so you can just write it m sub e like that. Alright? Now these are all the masses, so we know that E is equal to m times c squared, so to convert this to an energy we need to multiply by c squared. That is an energy. So it's the mass of the nucleus before minus the mass of the nucleus after minus the mass of the electron. So look at it. It's this mass minus this, and we're talking only about nuclear masses. But we can convert this because we know that the nuclear mass is equal to, we know that the overall mass of an atom is equal to the nuclear mass, and it's equal to the nuclear mass minus the, not minus, let me think now, plus the number of electrons times the mass of an electron. Very approximately, okay, very approximately. Okay, I know I've left out the B's and the B values there, but we don't need to talk about that. That means that the nuclear mass, m sub n, is equal to the total mass minus the number of electrons times the mass of an electron. So what I'm going to do is plug this back in here, just for the crack. There's no particular reason we should do that. It's just sometimes easier to analyze things when they're in these forms. So our Q value is going to become the following. It's going to become the mass of X, the actual mass, the overall mass of the total atom, minus the mass of Y, the total atom, minus Z times the mass of the electron for atom X, and we'll say minus, or minus times minus will give you a plus the Z number times the mass of an electron for Y, times the mass of an electron, this one here, and once again we want to keep this to be an energy, so c squared. Alright, so look, we said that m sum n is equal to m minus z times me. That means for the mass of the nucleus for X, we're getting mass of X minus the number of electrons for X, and for Y it's going to be the other way around, because this negative sign is going to be minus and plus, which is what we have. We have minus Y but plus the electrons here. Alright, and the other thing you need to realize is that if we look back up here, the protons for X is the protons for X and the protons for Y are different. So we can say the following. We can say the Z number for Y plus 1 is equal to the Z number for X. Alright, we can see that. If you add one proton to this, you get this. So finally we'll just plug that in here just to make life a bit easier for us. And if you just look at it, okay, that means if you plug that in, you're going to find the total mass of X minus the total mass of Y minus the mass of an electron minus another mass of an electron, this one here, all multiplied by c squared. Alright, so what else have I got to say about that? I don't really have anything else to say about that. So that is the energy release during a beta plus emission. Alright, so if you don't understand this, just look very carefully at what's happening, okay, and that should make sense to you. So next we're going to look at beta minus emission. Beta minus emission, and I'm going to pick up the speed of this because it's the same process really. So beta minus emission looks something like this. A zxn becomes a z plus 1 y n minus 1 plus an electron plus an anti-electron neutrino. So this time we have our Q value, the energy released, is equal to the nuclear mass of X minus the nuclear mass of Y minus the mass of an electron released, and this is all multiplied by c squared to make it an energy. And then we plug back in the next thing we do is we plug back in our overall masses, okay, in the same fashion we did a moment ago. So you're going to get the mass of X, the overall mass of the whole atom, minus the whole mass of the atom Y, minus Z times the mass of the electron for atom X, plus Z times the mass of the electron for atom Y, minus the mass of an electron, and this is all c squared. Alright? But the number of protons for Y minus the number of protons, let me think, what have I done here? The number of protons for Y, oh excuse me, I did that again. Number of protons for X. Just bear with me, I'm just looking at my notes here and after spotting a small typo. So it's number of protons for Y. What I've written is this plus 1. Let me think now. The number of protons for Y is equal to the number of protons for X plus 1. Sorry about that now. That was just my notes there, making a mistake, okay? So if we look at that, and if you apply that, what you'll find is that these three terms here equal 0. Alright, as a result of that, which means that you're left with the following. You're left with that your Q value is equal to the overall mass of X, the atom, minus the overall mass of the atom Y, all times C squared. And that's the formula for the energy release during a beta minus emission. And the last thing I'm going to do is just very, very briefly talk about electron capture. Now, electron capture is exactly what it says on the tin, where an atom captures an electron. Alright, so the overall result is very similar to beta plus. But we'll say this is where a proton that's already in your atom somehow catches an electron that's flying around in space. And if that happens, of course, it becomes a neutron and it emits an electron neutrino like that. So another way of writing it is that we have our initial atom, we add to it a single electron. If we add to it if we add negative charge, that means the positive charge is after being reduced, so we have Z minus 1, so the proton is being converted to a neutron, and we have N plus 1 here like that, and we must emit our electron neutrino. And you'll find that this process, although completely different in how it happens, has the same net result as when you have a beta plus emission. Alright, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends and subscribe to my channel.